First of all, what is metallic bonding? Metallic bonding can be defined as force that holds atoms together in a metallic substance, which means attraction between a positive ions and the sea of delocalized electrons. Metallic bonding is a strong bond, and the strength of metallic bond is proportional to the number of valence electrons and inversely proportional to the size of the atom. For example, the metallic bond in magnesium is stronger than in sodium because magnesium atom has 2 valence electrons and smaller, while sodium has only 1 valence electron and larger. Next, moving on to electron C model. The definition states that the electron C model is a model of metallic bonding in which cations are considered to be fixed points within a mobile sea of electrons. Metals can transfer electrons to non-metals and form ionic solids, such as sodium chloride and HCl. In addition, metals in the gas phase show that 2 metal atoms can even share their valence electrons to form gaseous diatomic molecules such as Na2. Atoms in metallic element are packed closely as possible. Therefore, each atom becomes attracted to the positively charged nuclei of the neighbor and become free from the attraction of its own. These free electrons are said to be delocalized over the entire solid embedded in a sea of electrons. The electron C also acting as glue holding the positive ions.
Now, let's talk about band theory of metal. We have valence band and conduction band, which are the main energy levels in the energy band diagram. So, valence band is the band of orbitals that are filled or partially filled with valence electron. Lower molecular orbitals are occupied by valence electron. Conduction band is the unoccupied bands in which electrons are free to migrate. Empty molecular orbitals that are higher in energy. And lastly, band gap is the energy difference between valence band and conduction band. As it shows in the energy band diagram for insulator, the band gap is large, while semiconductor have small band gap, and conductor, the valence band and conduction band is overlap. Current flows when electrons move from the valence band to the conduction band, and the amount of energy required to promote this will determine how well the substance conducts. And in metal, the valence band and conducting band are overlapping with each other. Moving on to the next topic, which is doping. So what is it? Doping is a process of introducing very small amounts of certain foreign atoms into the crystallities of a semiconductor to modify its electrical properties. So why do we use doping? Pure semiconductors like silicon or germanium have low conductivity. So with doping, it will create such charge carrier that will enhance its electrical properties. There are 3 main techniques of doping. First, diffusion. Dopants introduced to the surface at high temperature. Then, the impurities diffuse into wafer over hours like a spice permeating a stick. It is the most common doping technique. Next, ion implantation. Dopant atoms ionized and accelerated into the wafer. Precise doses placed exactly where needed, and wafer annealed later to incorporate ions. And lastly, in situ doping. In situ doping, which impurities added during semiconductor crystal growth. It also has very uniform doping concentration, and it will enable advanced structures like superlattice.
Next, semiconductor. Semiconductor is a material with intermediate conductivity between conductor and insulator. Conductivity can be controlled by energy or doping. And it is commonly used in electronics as transistor or diodes. We have 2 types of semiconductor. The first one is intrinsic semiconductor and the second one is extrinsic semiconductor. We go to the first one first. Intrinsic semiconductor naturally have a moderate band gap, and a small fraction of the electron in the valence band can be excited into the conduction band, and intrinsic semiconductor can conduct low current. Next, to the second one, extrinsic semiconductor. Extrinsic semiconductor is a semiconductor with added impurity, which is we call as dopants, to increase the amount of current they can conduct. there is N-type semiconductor and P-type semiconductor. N-type semiconductor is semiconductor that doped with pentavalent atoms, which is 5 valent electrons. For example, phosphorus and arsenic. N-type semiconductor provide extra free electron, and inside the N-type semiconductor, electron move through the structure and function as a charge carrier. N-type semiconductor, also known as donor impurity. P-type semiconductor is a semiconductor that doped with trivalent atoms, which is 3 valent electrons. For example, boron and aluminium. P-type semiconductor creates holes, which is missing electrons. And the charge carrier is effectively a positively charged hole and known as acceptor impurities. Next, to the p-n junction. It is formed by joining p-type and n-type semiconductor. The processes that follow after forming a p-n junction are of two types, which is diffusion and drift. There is a difference in the concentration of holes and electrons at the two sides of a junction. The holes from the p side diffuse to the n side, and the electrons from the n side diffuse to the p side. This gives rise to a diffusion current across the junction. And p-n junction also basic structure of diodes, and it is also allow current to flow in one direction only.
So next, the example of composite for semiconductor. The first one, silicon Si. For this generation, is most widely used. So second, germanium Ge. It used in early electronic devices in 90s or 80s. The third one, gallium arsenide GaAs. It has high speed and high frequency application. And the last one, for example, indium phosphide INP. In optical and communication devices. They use in optical and communication devices. Other than that, there's a few applications the semiconductor in our daily life. So the first application is electronic devices. For electronic devices, it used in transistor as switch and amplifiers. It is usually found in integrated circuits, ICS. So the application is using in smartphones, computer, or maybe television. The second one, solar cell. For solar cell, silicon semiconductors convert sunlight into electrical energy. It usually used in solar panels, renewable energy systems, and it also environment-friendly energy source. And the third one, LEDs. LEDs is a semiconductors emit a light when current flows. It always used in LED bulb, traffic light, display screens, and some people use it in car headlight. So for the conclusion, semiconductors are material with controllable electrical conductivity. They plays a crucial role in modern technology. They are widely used in electronic devices such as transistors and integrated circuits, as well as in solar cells, LEDs, sensors, and communication systems. Due to their efficiency, reliability, and versatility, semiconductors have become a backbone of today's electronic and energy industries.